Just to mention that you all have to click OK in the recording, otherwise you would not be able to write in the chat and things like that. So welcome everybody to this webinar of space infrastructure. The webinar is trying to cover the space infrastructure projects, the future needs and potential solutions for them. This is a webinar in preparation for the IAC special session that would take care in Dubai in October for space infrastructure games, which would be in the format of interactive game and reflections, and is planned for Friday at 9:45 to 11:15. The webinar is sponsored by IAF Young Professionals who support actively the special session, and with LightBridge Strategic Consulting, who is organizing and hosting the session. LightBridge is a firm specialized in business analysis for space investors and financial strategic support for space infrastructure projects. The reason for the young professionals to be here is because most of the space infrastructure projects are a multi-generational effort, and the young professionals have really an opportunity here to get on board early and to build an interesting, important, and stable career path for the next decades. The agenda of the meeting would be having in the 60 minutes, we will cover 20 minutes with John C. Mankins, who will have a presentation of upcoming space infrastructure needs and proposals. Then Dr. Peter Swan will cover 20 minutes of a launch system infrastructure, which is a space elevator and the Galactic Harbour. Then Kevin Barry will cover for 10 minutes economics of a space infrastructure projects. And then we will have 10 minutes for question and answers on open microphone as well. Just some brief bio on the speakers today. Dr. John Mankins is Vice President of the Moon Village Association. He is the President of Artemis Innovation Management Solution, which is a consultancy firm that supports and manages space innovation. He is in the board of the National Space Society and Space Canada. He has more than 25 years career experience in NASA and Jet Propulsion Lab, and he's an advisor in several new space companies. He's best known for writing in the 90s the first detailed definition of the technology readiness level, and he's the world leading expert in the field of space solar power. Dr. Pete Swan, who will be the second speaker today, he's the president of International Space Elevator Consortium, ISAC. He's a senior vice president of Galactic Harbour Associates, Inc. He's a faculty associate in Arizona State University, and he has built space subsystems such as the Iridium constellation and taught space system engineering around the world. He has many publications and 5 books published, including the Space Elevator System Architecture. The third speaker, Kevin Barry, is the co-founder of LightBridge Strategic Consulting. He's part of the financial subcommittee of the Foundation for the Future. He's an investment partner in BKG Enterprises with a master in real estate development, and he has presented papers in space debris and historical infrastructure economics.
Yep. And Eduardo is my other co-founder of LightBridge Strategic Consulting. He's also part of the financial subcommittee with me at the Foundation for the Future. He has 10 years of experience in an engineering multinational, managing a yearly budget of over 200 million euro. And he has previous success as an entrepreneur in IT startups and has an international background, living in 7 European countries in the last 10 years.
Okay, with all that, I think we're ready to go with you, John.
Okay, very good. Thank you so much for the kind introduction. It's a pleasure to be here with everyone this morning. My topic today is focused on the need for space infrastructure. And so I'd like to share with you just a few thoughts, a few visions for the future over the next 18 minutes or so. And I thought I would begin with this observation concerning Robert Goddard, written by the editorial staff of the New York Times in 1921. That Professor Goddard does not know the relation between action and reaction, and the need to have something better than a vacuum against which to react. He seems to lack the basic knowledge ladled out daily in our high schools. And this was the opinion of the magisterial and erudite leadership of the New York Times about one of the great leaders of rocketry in history and in the 20th century, who was then driven by this harsh ridicule to move to the desert and continue his experiments in private, where he would not be constantly poked at with sticks by intellectual gorillas. So those who are pursuing the future must be inured to opposition and be aware, although they may not always be right, nevertheless, it is worth the risk to make a better future. So with that, well, in 1963, this is the world that was envisioned, that the future would be rockets, that there would be space stations, there would be lunar landers, there would be weather satellites, there would be spacesuits, ships to Mars, a wide variety of things. And some of these visions have turned out to be true. Some of them have turned out to be false. And a great many important visions turned out to be missing because of key technologies that were not there at the time, some 60 years ago. So as it appears now, reusable launchers are absolutely an important part of our near-term future, beginning with the partially reusable launchers that exist already. The new era began only 6 years ago with the first flight of a Falcon 9 reusable. It's amazing to think how much our thinking and our perception of what the future will be like has changed in only 72 months now. And the future will be even better in terms of lower and lower cost, more and more frequent, more and more reliable access to space. One of the things that's been made possible that was not envisioned in 1963 is ubiquitous global communication. So mega constellations, a critical mission and infrastructure are all already being deployed. Starlink, of course, coming later, things like Kuiper and OneWeb. The idea that space is only for GPS, GPS unimaginable 30 years ago, but that space is only for GPS and bent pipe TV communications is rapidly being overturned. Next will be next generation government and commercial space stations around the Earth, following in the footsteps of Wernher von Braun back in the 50s. But also around the moon, and not just space stations where people will live, but also, as we'll discuss again in a moment, propellant depots and such like. Large space systems are rapidly becoming obvious. I think my own opinion, the last big kinematically deployed spring open telescope will be the biggest one, the James Webb Space Telescope. I think going forward, structural assembly, robotics, low-cost launch of extremely large masses, all of that will become so ubiquitous and so straightforward and so understood. No one would propose spending $10 billion in 15 years to make a open telescope again. Efficient and reusable in-space transportation is following fast, both nuclear and electric. And through the obvious miracle that we take for granted, it's only been around for 150 or 200 years, in-space refueling, local refueling of vehicles, so we don't use space vehicles only once, will transform cislunar space and the inner solar system. One thing that will be enabled by the combination of low-cost access to space and in-space transportation is space solar power, i.e. moving beyond the mega constellations to providing power to the Earth at an affordable price when and where it is needed to supplement terrestrial carbon net zero sources. And of course, again, I put in this illustration in the lower left that comes from a magazine 70 years ago. The idea of a mobile base, a mobile exploration outpost on Mars, part of Werner von Braun and Willy Leigh's vision, but also the idea of mobile and modular exploration outposts will make it possible to widely explore with humans and robots the moon, Mars, and frankly, any place we care to go that has a physical surface in our solar system. Beyond that is, of course, the mining of resources. I'm emphasizing, because of my work with the Moon Village Association, lunar mining with affordable transportation, access through affordable in-space transportation to cislunar space, space solar power, then mining the moon and other places for propellants, for logistics materials like water, and later the manufacture of systems will become far more straightforward and obvious to all concerned. However, we will not stop with the kinds of rocket propulsion that are available. I highlight here a couple of specific options. One, the Star Tram, invented by a good friend, now passed away, Dr. James Powell of the Brookhaven National Laboratory, and of course the space elevator, which will be a topic of Peter Swan's in just a few moments, as two options for getting off Earth at far lower cost than can be achieved with rocketry and with greater reliability, and also not just Earth, but other places. Maglev, electromagnetic launchers, not coil guns and rail guns, but moderate gravity, moderate acceleration launchers will make it possible for materials to be moved essentially throughout cislunar space, initially from the moon and later throughout the inner solar system. This was a concept which was first looked at by another good friend, Bill Escher, back in the 60s with his Lunatron, that's on the left. And then my update of it is the illustration done for Ad Astra magazine on the right. And in the longer term, sort of the culmination, I think, of many of these developments, and as far as my inner eye can see at the moment, other than talking about interstellar, which I won't do today, are true colonies in space, whether they're in zero gravity or partial gravity, such as on the moon, beginning with initial outposts and leading in due course to the creation of miniature biospheres. This is an intermediate step between initial outposts and eventual terraforming, which I view as being many centuries away, but the creation of small biospheres comprising many square kilometers of habitable volume, both in free space like an O'Neill cylinder or on surfaces such as on the surface of the moon. Those things are achievable with technologies we either have in the lab now or are envisionable during the coming few years, and could be done within this century. And so that's it, except to say that so the future today is certainly, it comprises what was envisioned in 1963. Those visionaries of 60 years ago didn't do such a bad job, but so much more. Thank you very much.
Thank you for that. Pretty good with the timing. I think we could go directly with Dr. Pete Swan, and then we cover all the questions at the end. Yeah, Pete, you should be able to unmute now.
Thank you for that, John. We'll now go and listen to Dr. Swan here as he discusses the opportunity that a space elevator provides to deliver mass, not just to space, but to really anywhere in the solar system at a high cadence. So, Dr. Swan, if you would like to share your slides, you can start your presentation.
Okay, welcome everybody. I really like the talk by John because he laid the foundation. The future is bright. We have so many opportunities coming up. We have rockets, and I love rockets. I've been involved in them forever. The changes in the reusability and Jeff Bezos and Elon Musk, we can't salute them enough. They are really changing the world. The other aspect going in parallel with their reusability is the commercial side. Because they're reusable, the price is going down. Because they're going to do more and more launches per year, the price is coming down. And we love that. That's really great. The space elevator community believes that we should come up with a dual space access architecture where we use the strengths of both. It turns out both the space elevator and the rockets have different strengths. They do different things. And to build the future that John was talking about with colonies out there, we need to have all the capability we can get. So what I'm going to talk about today is the remarkable future that I see in parallel with John about moving off planet and achieving great missions. So I got to hit the right button here. So the real kicker is there are a lot of dreams out there today. Turns out a lot of them are right here on the page, and NASA is going to put people on the moon, first lady, first whatever. They're doing a great job. They're bringing along international. That's another major thrust of the new century. It's international, it's commercial, and it's reusability. We have Jeff Bezos, who's really fighting to be able to do the up down on the moon. His little blue moon is a great little vehicle from the outside. It looks great. I cheated in Washington in 2019 when we had the IAC. I reached over the ropes and touched it. You know, that was illegal, immoral, and they didn't want you to do that, but I had to touch the blue moon. We have Elon Musk wanting to take 1 million people to the Mars and 1 million tons also. The Lunar Village is a superb articulation and discussion about what we need to do to move off planet and have a real destination in the near future. And then, of course, the granddaddy of all designs, the L5 colony and rotating cylinders, brilliant designs, really amazing. The question I want to pose to everybody while they think of the future, and this is really critical to our future, how much mass are we talking about moving to orbit? How much do we need to fulfill these dreams? And so that's what we're going to talk about. Well, let's start with the National Space Society. They want millions of people working off planet in a thriving community. I have believed in that mission since I was a young pup. That is a true mission that we have to fulfill. But whenever I talk to anybody in this particular field, they never say how many tons they have to move off. The O'Neill cylinder, and I had to look extensively in all the stuff on the web and download PDFs. I finally got a number for one of those little colonies, 10 million tons, 10,500,000 tons. That's a lot of mass when you believe that rockets will get you 2% to geo. And, you know, historically, they put 0.5% on the surface of the moon. Now, we'll do better than that, but not much. The movement of mass by rockets is inefficient. So if we want to do a lunar village, now I guessed at this. This is my 50 plus years of experience guessing at this, but it's a lot of mass to get there. Yes, I know we can use materials there. I have actually a part of a company that's trying to figure out how to mine the moon. So I understand that. But the point is, we're still going to have to move a lot of mass. Ooh, and then there's Mr. Musk's plan to go to Mars. I love his plan. I am behind it 100%. But he launches 100 metric tons on his little, or his big heavy lift vehicle in a Starship. But you have to remember, it's not the 100 metric tons that you would think about. The 100 metric tons that goes to Mars requires 5 launches in low Earth orbit to refuel and get ready. So it's really 5 launches to get 100 tons off to Mars. So the percentage of mass going to Mars is very, very small. And the space solar power, I'm behind Dr. Mankins and the Cassiopeia and all the other options. We must do space solar power. And we've got a lot of activity trying to support how we do this. But it's somewhere between 3 million and 5 million tons. So we're talking about tremendous needs. We must move off planet. We have to have a vision that takes us elsewhere. We have to look up from our location on the Earth, but we need mass movement. So if you're going to do that, let's talk about space elevators. I'll show a picture or two of space elevators, but basically it's 100,000 kilometer long. And we have a material now called single crystal graphene. There's also about 5 or 10 other materials that have been discovered in the last 5 years. Hexagonal boron nitride is the leading character in my mind, but single crystal graphene or white graphene is what the boron nitride is called. And you have 100,000 kilometer long tether, and you have electric climbers going up and down. We have the geo region where we're going to do a phenomenal amount of enterprise, refueling, building. John's comment about assembly in orbit is so true. We're going to build big things there. Then we're going to build things at the apex anchor and release them there. Interstellar is just logical to build our enterprise spaceship at the apex anchor and release it with high velocity. So our vision is a green road to space. We raise massive tonnage with electricity. So it's green road. In addition, we're going to have 6 of them, the current concept, and we sized out what that means in the sense of mass movement. The 100,000 kilometers of a tether rotating around the equator of the Earth gives us 7.76 kilometers per second at the end. We can be to the moon in like 10 hours. Now you're going pretty fast, so you better bring along a little rocket to slow down. So we love rockets, but the point is it's really going fast. We can get to Mars in 61 days. We have a bus schedule leaving from 3 galactic harbors around the equator, going to Mars. We can launch every day of the year. We don't have to wait for 26 months. Every day of the year, we take off to Mars, and it's 7.76 kilometers per second. You're leaving the sphere of influence essentially at 3 times what the rockets end up doing. So our study, go to our website, you can read all about how we are a green road to space, and we empower green activities such as space solar power. Here's a little comparison of what we estimate for the future. We estimate that when we have the first 6 up and they're doing initial operations, that'll be the minimum capability at the time, we can do 30,000 tons per year. That's 14 metric tons per carrier per space elevator per day. Now, let's put that in perspective. I spent 6 weeks going on the website and recording every vehicle that went to orbit that I could find. And I got to 22,000 tons. And by the way, most of that's the space shuttle. I counted the space shuttle as an orbiting object. It was a satellite. It just came back down and stuff like that. So 22,000 tons is all humanity has done in the history of lifting off to orbit. And we plan on doing 30,000 tons once we get initial operations. Now, once we ramp up and we have heavier tethers and we get going, we plan on having 170,000 tons per year. If you just look at the mass movement of space elevators, you must go forward with the risky project. We have risks. We know that. We've got to go forward and do it if we want to fulfill the needs of the many. So why do we need space elevators? Because we must achieve our dreams. So what we want to do is we want to combine with rockets. We love rockets. Rockets do a lot of things we can't do. Moving people through the radiation belt rapidly, stuff like that. We need rockets at the other end to slow down and rendezvous and land. But the rockets only deliver 2% of the pad mass to geo, period. And I've studied a lot of nuclear power and nuclear propulsion, and I've done that, and they're going to be really great. But you got to remember that's in orbit. So you got to get up to LEO to assemble all that kind of stuff. So the space elevators are green. Now they have a basic problem in that we're not here now. It's going to take a while till we're operational. I call it the conundrum of rockets. The question is, why would anyone want to deliver 0.5% to your destination? That's what Apollo did. They deliver in the recent summer launches toward Mars. They ended up and went and orbited around it and landed on Mars. We were launching less than 1/3% of the mass on the pad to land or rotate around Mars. So the conundrum is rockets is, why do we use rockets when we deliver such small numbers? The answer is, it's the only thing we can do. So we have to figure out how to beat that rocket equation. And the answer is, we skirt around it, we ignore it. We work on the outside of the rocket equation. We use electricity to rise above the ground. So the dual space architecture is our concept. Let's get together with rockets. Let's work with them, use the strengths of both of them, and we'll minimize that rocket equation limitation. So why must we do it? We must do this to fulfill the dreams of many. We want to move off planet. We want space solar power. We want those massive programs to be effective. The simple, elegant solution to beat the rocket equation is space elevators. Now, where are we? We literally have passed the preliminary technological assessment, readiness assessment. We're entering the engineering validation. We've started a company who's hired to build the space elevator. We're entering the testing phase. Now, we got a lot of hurdles. One of them is money. One of them is we got to get going. The material is there in the laboratory and will be ready in the 8 years before we get there. I believe we'll have the tether material when we're ready to deploy it. So the strengths, I'm not going to go over this list, but the bottom line is it's a permanent transportation access. It is a railroad track. It is a bridge. That's all it is. But the key is it moves a lot of mass. Here's a little study we did at the Arizona State University. We looked at what we could do if we left the vicinity of the Earth at 7.76 kilometers per second, the altitude of 100,000 kilometers rotating. Here's the answer. We cut the corner. We don't wait for the conjunction of the two planets to be appropriate. We do it every day of the year and then take a path. Now, some paths are 400 days long. That's when you're going to send your hammer and nails and heavy stuff. If you're going to send your pizza, you want to send it on the 61-day trip. And so the answer is, by really leaving the apex anchor at a high velocity, you really travel rapidly and you get to your destination. Rapid transit every day, massive movement. So the visions are out there. We need to fulfill the visions of humanity, move off planet, create colonies, create a space solar power. We need to do that. But nobody in the community, if you sit down and talk to them about their dreams, says, how much mass do I need? It took me a long time to figure out the total mass for the L5 colonies. A lot of time, because they didn't want to talk about it. It's huge. So the question is, how do we do that? And the answer is a dual space access architecture. So anyway, thank you. That was my quick review of where we are on space elevators and why we need space elevators. And the bottom line is, if we want to dream, we've got to move mass. Thank you.
Thank you, Dr. Swan, for that overview. And one other point I would just add about the space elevator, which is fairly interesting compared to rockets, is that while rockets, which is shown in this lovely drawing, they're basically a pyramid of fuel going into the rocket, whereas the space elevator, the delta V that you're able to achieve just leaving it like the end of a ball on a sling is almost mass independent. So it allows for mass transfer anywhere in the solar system with that kind of velocity, which allows for much bigger projects to be sent out economically than you could otherwise even feasibly do with rockets. All right.
Thank you. Yeah, that's excellent. Let me just make one little thing. I had a lot of fun. I had an intern last summer well, 18 months ago. And she was assigned the duty of figuring out how to get mass to the apex anchor. So she was calculating all this kind of stuff. And she asked if she could do a little painting. And I said, well, of course. So she did the painting on the left in acrylics. She's an artist as well as an astrophysicist. And I thought that was hilarious. So anyway, she's let us use that. And so we're using her little depiction of our strategy for the future. But it's remarkable that a senior in college has a perception to understand the strategic approach of something like this. She really did a great job.
If you would like to find more about the space elevator, ISEC has quite a bit of information in all the reports. They have exhaustive documentation going through all of this and collecting together, I believe, over 600 scientific papers into their various reports. But moving on, Swan, if you could stop sharing your screen so I can take over. Thank you. All right, so one of the first things I wanted to kind of mention here is that there's an important distinction when you're thinking about what is infrastructure and how does it work. And that is this critical difference between cost and price. That if you are an enterprise like this one selling fountain drinks, or if you are an infrastructure project like building the many highways that are all over the United States, both of these benefit from having lower cost. If I can build more highways or produce more soda machines, it's always good. But the economic incentives for these two types of industry are very different. That if in enterprise setting, they are motivated to increase the price that they're willing to charge a customer as high as possible in order to generate a profit. That's essentially how enterprise business works, that a higher price compared to a lower cost leads to better margins and you have a more successful company. But infrastructure doesn't work quite the same way. Infrastructure is actually benefiting from having a price which goes down and down and down, that the purpose of infrastructure is to lower transaction costs. And indeed, as a business, highways don't really make sense in the United States. They're free for everyone to use. You do pay a gas tax on them, but you don't actually have a price for utilization. There is no marginal cost for individual users. And that's because they aren't trying to eke out a profit in the same way that enterprise does. So that while the cost of infrastructure certainly is not zero, they're quite expensive to build and maintain, the price can be because it's not trying to be driven on a profit model. And this is because of some of the secondary effects that you see in infrastructure. This is just an arbitrary graph here showing that for a linear decrease in price, you see an exponential increase in the amount of utilization. This is partially due to the supply demand curves where you keep lowering the price, you're going to get more consumers, but it's also due to something called a network effect, that by simply connecting together more and more nodes, and this can be represented here, it's old telephones, but it could be businesses, homes, anything that you're having on the network, the more connections you have, the more exponential increase in the number of connections. So just shown here, going between 2 and 12 phones, you see an increase from 1 to 62 connections. And this means that as you get more and more utilization of the system, you're increasing economic productivity and economic success. This allows for interesting features like taxes or marketing, in the same way that Google search is free, but they are one of the most profitable companies in the world because they're able to benefit on ancillary benefits from a growth in economic productivity and utilization rates by lowering their price below their supposed costs. We've seen this happen in the last century with aviation in particular, that in the 1940s, a flight between Boston and Los Angeles was an intense ordeal of not only did it cost $4,500, you had to make 12 stops over 15 hours to get between those two cities. Today, this is 2015, but today your cost is below $500. It's a 6-hour flight, if that, and you have no stops. It is a nonstop flight from one to the other. And this price reduction for the consumer is only about it's only a tenth of the original cost, not even. But we've seen in that time period, utilization has gone up almost 80-fold, going to increasing both in freight and in passengers. These increases are critical to the understanding the way that infrastructure works. That it's sort of like the chicken who bakes bread, that the little red hen takes and wants to bake the bread, and nobody wants to support it at the beginning, but everybody's wanting to have the benefit at the end. Infrastructure always looks good in hindsight because you see all the economic productivity and the benefit of having it built. But understanding the economics of doing it in the first place is about understanding those intangibles and those ways in which infrastructure functions aside from classical business. And that when you analyze infrastructure projects as a business, they always appear to perform poorly. Our analysis at the games, and we're going to be talking about in Dubai, is to really examine how these two things play together. That when you're trying to solve the problems that have been brought up by both Mankins and Swan today of moving mass amounts of cargo, personnel, and objects to space, you need to find a way to do so productively and economically. And that's where we feel that infrastructure really plays an important role. Some of you may be thinking in here, well, we've already seen the cost of space dropping so quickly. I mean, look at what Starship is going to deliver. They're 4 orders of magnitude below what the space shuttle did 17 years ago. And that's true, it's great. But the difference between having a commercial business, which is going to try and have the highest price the market will bear, versus building an infrastructure project, which can deliver boring commodities, not people, not important scientific equipment, but just all the iron and water and things that we're going to need to build the first recon bases before we can get to in situ resource utilization. Before we can even get to that point, we're going to need a huge amount of seed mass. And that infrastructure is the way that this is achieved. Transcontinental Railroad is a good example of what this looked like in the United States, where it was possible to travel between the East and the West Coast in the United States. You could take a wagon train, took you about 6 months, you can get there. But when you built the Transcontinental Railroad, it changed not only your ability to get there in the week, the number of businesses and economic opportunities that created. You could sell California oranges on the East Coast. You could take and commute from one end of the country to the other without having to risk your life. That you could form these business partnerships that bridged an entire continent. These are the kinds of things that infrastructure enables. And that when you build real infrastructure, it is a lattice on which an entire economy can build up and around. That's the real value of infrastructure. It's the cities like Denver that were along the way, the mining towns that became big cities, and all the ancillary effects you get from having a corridor of infrastructure with cheap, efficient, reliable transportation, which facilitates the growth of that burgeoning economy. That's what we're really trying to see in space. And that's why we believe that even though there's fantastic developments in rockets, they have their place in delivering high quality goods, but infrastructure is going to be essential for building a true economy in space. And with that, I would like to kind of open the floor up here to have our speakers answer some questions from the group. I know people have been writing in the chat here. I've tried to answer some of them, but if you just keep typing your questions, we'd love to answer them.
In the meantime, I was collecting some of the ones that they were still not answered. From Adele Khan, we have one that says graphene is carcinogenic. Has anyone figured out a way to make it safer, graphene? And then we have an answer for that.
It turns out that we, the International Space Elevator Consortium, are working with the University of Manchester, and the University of Manchester is where the Nobel Prize was awarded for the discovery and understanding of two-dimensional materials. And that's where single crystal graphene and white hexagonal boron nitride are being worked on. Now, it turns out they're being developed in China, South Korea, a few places in the US, and University of Manchester in very rapid form because of the promises. yes, indeed, anything in powder form is going to be a real issue, but we are not talking powder form. We are talking about a molecule that's a kilometer long, 1 atom thick and 1 meter wide. And so that's not very carcinogenic. Of course, the development of it would have stuff in the air and stuff like that. So the answer is development of the material will go under the same hazardous conditions as any material development industry. So they'll be dealing with this safety issues big time. But once it's a cable or a tether, I don't see the issue of carcinogen and all that kind of stuff, because it's the strongest, lightest weight material known to man, like 1,000 times better than steel in the strength to weight ratio. And so now that's my neophyte engineer answer to a scientific question. If you want to pursue it, please go to the University of Manchester or other places that are studying it, because they'll know a lot more than I do.
In regard to the space elevator specifically, I mean, the current design is that the graphene ribbon would be pretty much exclusively above the atmosphere, that it connects down, and then you have the last 100 kilometers or so probably would not be the graphene sheet in any case. So there would be almost no potential contact once it's actually in the elevator. Its application in many other industries is actually going to be a, I think, larger concern that will be solved externally to the space elevator.
Okay, we have other question here. Let's cover a couple of other. Well, there is a comment from Chris Smedley saying that the network effect is factorial, not exponential. Just a note there. Then also from Adel Khan, we have a question on why is the ship in the sea for the space elevator attached to the tether instead of on the ground?
Well, it turns out we have two issues with the location of the ground station, the Earthport. First is, if you're on the equator, you get 100% of the rotation and you get the most mass delivered on the space elevator. You rotate up in latitude, it's a cosine function and you lose mass delivery. So you almost have to be on the equator. And the second is, we're going to put it at a peaceful spot in the Pacific where it's been no lightning strike in 100 years, no rogue waves, no hurricanes, no winds, all that kind of stuff. There's really a delightful place in the Pacific. Actually, it fits right under the skinny location in geosynchronous, where there are very few satellites because of their location and transmission between the continents. So it's really a nice coincidence that we'll be in the Pacific, where we won't have too many threats in the sense of environmental. Of course, we got to plan for them all, because, you know, anytime you do any location with people, you have to plan for the worst. But the answer is, we're planning on putting it there. Now, there is a dominant reason we're going to the middle of the ocean, and that is, it's going to be, you pick a number, $18 billion enterprise. And you would not want to put that located in a country that might not appreciate the commercial thing and nationalize it or something like that. The US and other countries have had that happen. So international waters, nice clean rules, you know what you got to do. One of the funny ones is, you must move your ship if somebody comes along in a sailing ship. So all kinds of little rules like that. But the answer is, everybody understands international waters, straightforward rules. If it's your activity, you know, it's your stuff and all that kind of jazz.
Okay, another one on space elevator. I'm going in order, one by one. Is this space elevator being designed in a modular fashion? Because a cascading failure could be bad.
It's like a bridge. You really can't use it until it's all done. So there's almost no scaling factor. Everybody says, well, let's put it on another planet or something. I wrote a paper a while back that said, Earth, Mars, Moon, where should we have the first space elevator? And the answer is very simple. We should have it at all locations in the future. John's vision of the future is, we're going to have a lot of movement and mass and everything else. Space elevators would help that. The kicker is, we got to get out of the stinking gravity well we're stuck in. So we're really not going to have robust activities off planet until we can get out of the gravity well. Now, if we can use anti-gravity, if somebody can come up with that, or another approach, I'll buy into another approach if somebody can say they do it better than space elevators. but we must beat the gravity well of the Earth before we can really have robust movement off planet.
And, just the sort of the corollary of that, long term, ultimately we would try and be using resources outside of Earth's gravity well. But even that first plant, that first mining facility, there's still a lot of seed mass that needs to get there. And even those masses, as Swan has discussed, are in the, hundreds of thousands, if not millions of tons, which makes doing it with rockets kind of impractical. If you took and launched a Starship at a rate of, 3 a week, you would need 187 years in order to get the amount of mass Elon wants on Mars. It becomes impractical to have that many launches, and we don't really know what the upper bound of how many rocket launches we can do are, but there is definitely an upper bound which will eventually be found. Whether it's a bureaucratic, technical, environmental limit, that's a little harder to parse.
Okay, next question is coming from Naveen Raj. He mentioned, how are you going to come over the Van Allen belt with the galactic radiation in the space elevator? And there is another one that maybe they can be covered similarly, is what are going to be the safety protocols inside the space elevator?
Okay, the answer is we've got two approaches. One is with humans and without. Let's go with the with humans. The Japanese Obayashi Corporation, remember, commercial, designed the space elevator in 2013, and they said they're going to have humans. And so they're going to have redundant tethers for duplication for safety. They're going to have massive tethered climbers, 100 metric ton tethered climber that's going to shield all the people so they go through the radiation belts in a shielded manner. So the approach, if you're going to take people, is that way. The International Space Elevator Consortium has a philosophy that we're going to do initial operations first, and we call that robotic cargo. So it's all cargo. And so, of course, if you have sensitive equipment, you'd want to shield that. But that's your responsibility as the customer. The vehicle and everything will be going up and down through the radiation belts. And we've got a lot of years, 70 years of practice on how to work in the radiation belt. So we can do that. But you're right. If we send people, we're going to have shielded and all that kind of stuff. That's why I believe the dual space access architecture is the right answer. Let's use rockets to move people. Let's take the people, put them in there, go fast through the radiation belts like the Apollo, and like Dear Moon that's coming up, Elon Musk taking a crew up there. And we've got NASA doing it. Everybody plans on going through the radiation belts rapidly.
And I mean, long term, there are lots of ways to deal with radiation. Water is in particular a surprisingly effective method of dealing with it. Every 7 centimeters of water, you more or less cut your radiation exposure in half. If you have a 2-meter sphere of water and you're on the inside of it, you experience less radiation than you do anywhere on Earth. Including if you jump into the pool around a nuclear reactor, you actually have less radiation exposure until you're within a few feet of the reactor itself, just because of the amount of protection you get from water. So resisting radiation is not particularly difficult if you have a system where you have an efficient means of moving large quantities of mass, because you can just bring water, which is pretty ubiquitous on Earth. And that's just the really simple method. There are better ways, but that's just one really, really easy way to do it.
Yeah, another silly thing that was reported that your green garbage bags that you take your trash out every day in has remarkable radiation shielding effects. I haven't pursued that, but that was an interesting scientific paper. And the question is, how many layers of garbage bags would you need? I don't know, but it'd be an interesting puzzle.
Okay. Next question is from Joe Rauscher. It's for Space Solar Power. He says, John, what feedback did you receive from the United Nations and your Space Solar Power presentation on the 1st of September? And then also, John, you were commenting something in the chat. Maybe you want to cover both of them.
Yeah, so the just for those who are not aware, on the 1st of September, the National Space Society was able to make remarks at the meeting of the Committee on the Peaceful Uses of Outer Space at the UN. And this year we chose to make our remarks on the subject of space solar power. We provided an update to the COPUOS on the status of space solar power and posed a question to the COPUOS of whether or not they would be willing to work, asking whether or not they'd be willing to work with the NSS and other organizations in looking more formally at space solar power in the coming months. We have not received any response as yet, but given that it's only been 2 weeks, and they had a lot of other business on their agenda, I would be surprised if they have even thought about it yet, Joe. So, and the other question that was posed we were chatting about was the use of the moon. And there's a wonderful blog written by a former NASA engineer, Edgar Zapata, that I would recommend to everybody. And the comment was that from Chris Smedley, that Edgar Zapata had mentioned that lunar source resources had a leverage of 3 to 4 vis-a-vis Earth-based resources. And I would just mention that the big difference there is, of course, that the where you plan to use the material in low Earth orbit, the delta V to go from Earth to low Earth orbit is about 9,500 meters per second, taking into account air drag and gravity losses and so on. In low lunar orbit, the delta V, the energy to get from Earth lunar surface to lunar orbit, is about 1,850 meters per second. And so that's a difference of like 4 to 1, 5 to 1 rather. And the delta V is in the exponent of the rocket equation, which is an exponential equation. So that's a really significant difference. But as you move away from low Earth orbit and you move away from low lunar orbit, it really depends on where you're going. And the big shift in the paradigm, I think, comes when you've got electromagnetic launch from the moon, and the cost, as Peter says, for space elevator is the same for the moon. If you can launch everything from the moon for about 2,000 meters per second to anywhere in cislunar space, and you can do it electronically, electromagnetically with just solar electricity, and all you need is the rocket propulsion to stop you in geo or at the libration point or wherever it is you're going, then that really is transformational. I think that happened sometime fairly early in this century, i.e. by like 2050 or so, because it's just such a powerful opportunity for whoever does it.
Mm-hmm. Yeah, and there's certainly so many projects that can eventually be built in space, which are beyond the scope of our talk today. I mean, there are very interesting mechanisms to do it. And the more that we can accelerate the transition to having a commercial space environment where you can have not just resource exploitation, which is sort of the first tier people think of in going to space, but establishing those other pieces of having scientific, commercial, enterprise, the other aspects of the economy all begin to play an increasingly important factor. As of yet, there has not been really any reason to have a space-to-space transfer. We have just the very briefest glimmers of it, starting with Northrop's refueling and repositioning on the satellite. But this is, most of the space economy to date has been about being in space, looking at Earth, and moving humanity towards the transition of having things in space, for space, or in space between space objects is the long-term goal of all that we're talking about today. And how we get from point A to point B is we need to build strong incentive structures and infrastructures that are able to facilitate mass movement into space in a safe, reliable, and consistent fashion. And all of the above is probably the correct answer. I mean, as per market economics, there is no silver bullet here. Even the space elevator in this conversation will be great, but it doesn't do everything perfectly. It can't really deliver mass to low Earth orbit hardly at all. But it is able to deliver huge mass to GEO. And from papers we're going to be seeing at IAC this year, it's going to be to deliver mass independent payloads at over 17 kilometers per second to fling it out of the solar system in weeks rather than years. These kinds of phenomenal energies that it's able to bring to bear are something that we're going to need if we want to go further afield, start colonizing the moons of Jupiter, Saturn, and exploiting the asteroid belt in the solar system. And I think that our purpose here today is not to restrict the number of options available, but to showcase how important it is that we address and look at how do we solve these next problems? How do we go from having our current paradigm of sending out covered wagons into the far west, and we need to switch to having that transcontinental railroad, that highway? How do we make it so that we have a good way of actually connecting the country? And in this case, the solar system together. And we'll show you in our panel in Dubai here, and you'll have the opportunity to play live games where you can experiment and see how it is to be an infrastructure project competing with commercial business. It's not all sunshine and roses. There are definitely benefits to both methods. And we want to showcase though, and we hope to see many of you there. If anyone in particular in this call is going to be showing up in Dubai and would like to work with Eduardo and I to sort of curate and run this event, we would love to have you. And you could please, we'll provide our email along with the recording after this call so that you can all see this. I believe people have been asking for the presentations as well. We'll make sure to get those from both Swan and Mankins as well. And
so we have the emails that you have used for registration, and we will send this information, and also we will also use social media like the young professionals and others to share this information.
Mm-hmm. And please,
okay.
if any of you want to continue this conversation, keep in touch. It's kind of what we do. So.
Yeah, maybe a couple of extra questions. We have time left.
Got a little bit of extra time.
Yeah, Chris Medley was making some inputs in there. One of them, which maybe is relevant, is has anyone in this group explored the possibility of orbital rings or others? We were also discussing the other day with John Mankins the possibility not only orbital rings, but also on a levitation train as well. Would be similar to orbital. I don't know if you want to comment a little bit on those concepts.
So just to, just from my perspective, I actually pushed on that noodle, pun intended, a little bit with NASA's NIAC program several years ago. And because if you build a ring around the moon or a ring around the Earth, or better yet, free space rings, then you have the opportunity for extremely high exit velocities. It's like a slingotron, but out in space. And you can basically reduce travel times anywhere in the solar system out to the Oort cloud to manageable travel times with manageable G loads. I could not get them interested. It was too far beyond what NIAC was willing to think about these days, which I think says that their process is broken. Because
it's the same as your Goddard. You'll never get rockets into space.
Yeah, the original study on space elevators back in the 90s was funded by me when I ran the Advanced Concepts program. But these days, the idea of an electromagnetic ring that would allow us, and you could build them in the inner solar system, near the Earth, inner solar system, outer solar system, anywhere we wanted to go, we could build a ring out of local materials and then be there in as few as weeks and as many as years. Nah, that's crazy. Can't do that.
Yeah,
so,
I agree with John. The answer is really exciting. I only asked the same question I posed in the whole presentation, which is how much mass do you need to do a orbital ring? And the answer is huge. But But, you know, I don't want to stop the visionaries. We come up with what we want to do, and then we figure out how to do it, because that's the real kicker. That's
Now,
engineering.
but Phobos and Deimos are conveniently located at Mars, Peter.
Yeah, that's
You don't have
true.
to go. You don't have to go very far to aerosynchronous, and you don't have to go very far for the mass you need for an orbital ring at Mars.
Well, that's true, but you got to get all the mass to get all the equipment. Anyway, next point is, I really think that the interesting point John brought out is there are ways to have extreme velocity in our region of the solar system, so we can go to the Oort cloud and places like that, and interstellar. We recently had a paper done by the Arizona State University looking at ways to release from the space elevator. And he actually showed, with new concepts on the end effector at the end of the space elevator, that you can have enough velocity to escape the solar system without using any gravity assist. And so that's a great velocity. And it was quite an interesting academic paper. Once again, the implementation of those concepts would be the next level beyond our first space elevator. It's a very sophisticated next step, but the velocities are remarkable.
And it sort of addresses Adil's most recent question here of, it is essentially what that would be, is you have the space elevator and then you have a second one spinning along
Right.
top. One of the interesting physics problems to solve with the space elevator, as is addressed in that paper as Swan is referring to, is that because of the Earth's sort of being rotating around a different axis, its inclination makes it so it's not in line with the ecliptic plane, and taking and having the sort of tether on the end in order to fire it back into the ecliptic is really important to making a space elevator work as well as it does. Otherwise, you're sort of ending up, 22-ish degrees off of the ecliptic, and you need quite a bit of acceleration to get back to where you need to go. And that problem can be solved, but it is better if you can sort of compensate for it on the end. And that is sort of, once you have a space elevator, lots of these ideas really start to make sense. And that's really the thing, is that it serves as a keystone project, that any major access to space, including what Starship is doing, any major change in access to space is going to have a fundamentally dramatic effect on what is possible in space, what makes sense economically, and how you can get there. And it's all due to this idea that as you have a linear decrease in the transaction cost for getting space, and that's not just the price, that's also the sort of intangible costs of how likely are you stopped by weather, how safe is it, how all those string of costs. As you have a linear decrease in the cost of getting to space, you have an exponential increase in the economic productivity. And what that looks like is like, trying to predict the future. There's a whole bunch of, we can speculate and we can talk here today about what could be and what might be, but at the end of the day, it is a moving target. And as we get better approaches for getting to space, we know it's going to be better. It's going to be bigger, and there's going to be new ideas we haven't even thought of that are going to be able to exploit these new technologies and these new economic regimes, where something that was impractical, we had 17 years ago with the space shuttle, the cost of getting 2 gallons of water in space was $100,000. With that same $100,000, you could now get a pool of water in space. The amount of difference that creates in terms of what makes sense and how do you, is it worth spending, hundreds of millions of dollars developing a water recycler, or do you just bring 10 times as much water and not worry about it? These sorts of changes are very interesting to follow. And that's what we're really trying to push for here, is that infrastructure, getting to space, however you do it, is going to make it so that space is a better place to work in and to expand into and to leverage all these ideas we've been talking about today.
Okay, I think the conversation is very interesting, and I think we should be able to continue it in Dubai or off the record as well. I just wanted to thank you, everybody. Just remember again that you can contact for all the, so there are some engineering questions that weren't covered that you can contact directly Swan for the engineering validation phase of the space elevator. then with John Mankins, Millage Association, Space Solar, and everything else, and also with Kevin and I, everything regarding infrastructure, economics of space. Yeah. So thank you very much all for your participation. And if you want to have some closing thoughts, John, Kevin, or Pete.
Go ahead, Pete.
Just that it's been a great event. Thank you so much.
Yeah, I'm just envious of having young professionals getting together. We didn't have much of that in my day.
Shane, you didn't have Zoom calls 40 years ago.
That's true.
Thank you all.
Okay. Well, thank you all, and hope to see you in Dubai or via email. And that's Jose Lidia.
Thanks, Eduardo.